It's actually my first talk at TU Braunschweig since I'm here in May this year. I started the junior professorship of the same title of my presentation. And I want to give you I want to share my interpretation of this topic with you and want to warn you, it's a conceptual talk. So I want to basically show you the concept, the ideas, how machine learning, numerical simulation, measurements can interfere with data-driven modeling and simulation with a focus on mechanical systems. Now my cursor doesn't want as I want. Okay, but I can use, no, I cannot advance my slides. Okay, but with the mouse it works. Okay, so here's the outline of my talk. First of all, I want to talk about virtual process planning for additive manufacturing. This is, as Manfred said, the topic of my PhD, and this is also my personal motivation to have a look into data-driven methods that motivates for me the need for digital twins. I will address physics-informed neural networks, which is a way to combine numerical simulation and data-driven methods. This is ongoing work also of our group at the Institute for Computational Modeling and Civil Engineering. In the fourth section, computer-aided medical diagnosis, I want to present a current student work, which is a good motivation for physics-informed neural networks. So it's rather a long-term goal, and also current work is here on computational homogenization with CNNs, which is also linked with the virtual process planning for additive manufacturing. So first of all, additive manufacturing, what is it? Why do we need it? In my PhD, I was focusing here on a laser powder bed fusion process. This is a typical machine. What we see here on the left-hand side, in common to all additive manufacturing technologies, is the principle to build parts layer by layer. When we have a look into a machine, we see here's a sketch of the typical machine. The processing consists of 3 steps. Of course, first we have pre-processing, afterwards we have post-processing, but the general processing is an iterative process. We spread layer of powder onto the build platform, which we see here from powder feedstock. Then we have laser irradiation of the desired portions of our powder bed. We lower the build platform once a layer has been processed, and this process is repeated and repeated all over until a 3-dimensional part is built. Post-processing, first of all, includes the removal of unnecessary powder. Then we have optional heat treatment, polishing, whatever is desired and necessary. Here's a video of the process. We see a powder bed which is partially irradiated by a laser, and once this layer has been processed, a new layer is added, and this process is repeated until the part has been built. There are several reasons why to use additive manufacturing. The first of all, which is often mentioned, is that this process is cost-effective for small lot sizes, so we can individualize products. We do not need to adjust a manufacturing plant for one specific individual product. So this is an advantage over casting, for example, or other metal cutting strategies. We have the ability to, this is basically a strong advantage. One advantage, we can create designs. We have a huge freedom in designs. Thereby, we can realize products that cannot be realized by other manufacturing techniques, for example, undercuts. And the advantage which I want to focus here on is the potential to realize functionally graded materials, so-called FGMs. In these FGMs, the structure and composition varies locally, and the goal is when we can basically tweak this microstructure, we can customize material properties locally. So this is shown here in the sketch. We see properties, a function of the position inside the part. This is the basic concept. And an example how the process influences the final part properties can be shown here in this video. It's fused deposition modeling. So a filament is deposited in this direction shown here. We see now these white stripes. This is actually where the part fails. So the process has influenced the part properties. And this was the motivation of my PhD, basically, and of many other efforts to simulate this process, to virtually design functionally graded materials, to virtually improve this process in order to manipulate this process. What we usually do with numerical simulation, we think about a structural simulation, we want to study performance. And performance is a function of topology and also a function of the material properties. We can then apply topology optimization, we can apply, we can perform parameter studies. This is what we usually do. Now, when we want to really realize functionally, when we want to plan the process, we need to consider process simulation. And the process simulation here is performed on 3 scales in selective laser melting or laser powder bed fusion. We have first of all the part scale shown here. We can study residual stress and overheating. This is an example for residual stress formation. We see a deflection here, which is caused by residual stress, residual distortion. This is of course undesired, so it has an effect on the topology. Another effect on topology is overheating. Blue region here is powder, unmelted material, and the red region is melted or solidified material. Of course, in the powder we have voids, so the powder isolates. The heat cannot escape as well as when we melt here over the solidified regions. So heat gets trapped, and then we can have these undesired enlargement of the melt pool. The next scale is the powder scale. Here we can study voids, we can study surface quality, as we see here. We have an uneven surface. This is mostly due to surface tension effects. And on this powder scale, which is now here of very small, 300 micrometers, where there's 1 millimeter, we can study the temperature distribution quite precisely, and this temperature distribution then influences the microstructure, grain growth, and nucleation. We see here a phase field model, we see cellular automata models, and using these models, we can basically study material properties. Now, my PhD was focusing here on this powder scale simulation. State of the art at the time when I started in 2016 was a code from Lawrence Livermore, which consumed on the order of 100,000 CPU hours for a single laser trick. So this was basically the starting point, and of course we did not have the computing facilities of the Lawrence Livermore, so we had to do something different. The first of all, which we can do in modeling and simulation, is the modeling part. In this laser powder bed fusion process, we have the effects of heat input, heat emission to the surroundings, of phase change from powder to liquid, and then the solidification. We have surface tension in the melt pool. We have the recoil pressure, which is shown here. Evaporating metal might indent the melt pool, and we have residual stress formation. And over these effects, there's the need to understand the process structure property interaction in order to be able to manipulate process parameters. The challenge here is the complexity. We have more than 100 parameters in the actual design. This is this is a number reported in the literature from a PhD thesis. Modeling of the physical effects. Now we have the equations of continuum mechanics. On the top, we see the momentum equation, and here goes in residual stress formation into the stress tensor, and also the phase transition affects the stress tensor, but the phase transition also affects here the heat capacity by means of a latent heat term. We have the heat input, which can be modeled as a volumetric heating source. We have surface tension and recoil pressure accounted for as Neumann boundary conditions, and we have the heat emission to the surroundings also accounted for as Neumann boundary conditions. On this modeling aspects, we published a paper where we developed a novel phase change model from powder to liquid and for solidification, which can capture all the effects of melting and solidification. We have developed a ray tracing scheme for measuring methods, which helps to identify the free surface and then distributes the laser energy in the proximity of the free surface. But the last one, which I want to focus here now, It's an SPH, smooth particle hydrodynamic simulation, where we consider the non-molten particles as rigid. So basically, we neglect here the solid mechanics, and I want to illustrate this a bit further. What we've seen in this video was the generation of a particle distribution with the discrete element method. So we consider here the particles as rigid. For each particle, each particle is represented by one discrete element. And this is only weighted for the powder deposition. But in order to display basically the melt flow, we need to discretize further. We need to discretize these DEM particles by SPH particles. And this is shown here. We have a smoothing length H, and this is then a support domain or kernel where we can define our approximates. So the good thing is that we can realize here arbitrarily curved boundaries. This is a huge advantage about mesh-based methods. And I want to show you next result. So this is a video of the actual process simulation then. We can display arbitrarily curved boundaries without locking. So we can remove solid particles from the momentum equation and only solve the energy equation in the solid domain. And this reduces the actual computing time down to 18 GPU hours per simulation, and which is a huge speed up compared to the 100,000 CPU hours of the Lawrence Livermore back in 2016. For this simulation, we plan to apply this simulation also on polymer sintering and couple it to crystallization simulations. And this is topic of an BMWI proposal, which is currently under review. So we've seen we neglected something in the power scale simulation, that is solid mechanics. And the question is, how about, we want to have a complete image basically of the entire process. So this is the power scale simulation. We have a different source of simulation. That is the part scale simulation. And the question now is how we can make this information we gather from the simulation useful for the actual machine. What is currently happening is that we have an expert who can gather information from different simulations, from the powder scale, from the part scale simulation, also from microstructural simulations, from experiments, from experience. And so he has to basically decide, he or she has to decide which information to pick and how to deal with it. Would be, however, very helpful for the expert if he or she could add some design assistance here, which would help to implement this knowledge gathered from the powder and part scale simulation directly into the machine. What we need for that is, in my opinion, that we need to not focus on the coupling here of the different scales in a numerical setting or the standard modeling setting, because all the information which you take here from the powder scale is then averaged on the part scale. So we should rather focus on virtual process maps for each type of simulation. And from these process maps, we can then build a data-driven design assistant, which helps to bring this information into the machine. And the expert has then time for creativity and other things that humans are more good at than interpreting data. So I want to focus a bit on the complexity of this virtual process planning. So I said in the beginning that we have so many parameters. The thing is here that we have, when we want to vary the influence of, when we want to study the influence of laser power, let's say we perform 30 simulations, which consume each on the order of 18 hours per simulation, which I said is quite quick, then we have a total of 540 hours. Same thing when we vary the laser scan rate, but when we want to study the influence of the entire parameter field, then we need to perform 30 times 30 simulations, and we end up with 20,000 and more hours of simulation. And the complexity increases when we consider the influence of more parameters. So we need to somehow find a way to identify optimal parameters, and for that we need to reduce the number of necessary simulations. Here's an example of the definition of an optimal parameter. It could be, for example, the gap between two particles. with a goal to simulate or to create highly dense parts. So we want to minimize the gap in order to have a fully dense part. And then the gap is a function of the process, and the process is a function of the parameter sets. Parameters here, laser power and velocity. And then we have two options. The first is we apply genetic algorithms, and we search for the optimal parameter, the one and only optimal parameter set within this complex gap function, which is a function of the process and a function of the parameters. Our genetic algorithms are evolutionary algorithms. We create random offsets of parameter sets, and then it's an iterative process where this cost function, this gap function, is always evaluated, and then new parameter sets are created from offsprings of the previous generation, and new random parameters are introduced into the algorithm. So it's a gradient-free optimization strategy, but it only helps when we want to look for the one and only optimal parameter set. What we are rather interested in might be a data-driven surrogate model. So here we seek for an optimal representation of this gap function. So we want to build a data-driven surrogate which helps us to identify this gap as a function of the parameter set. And yeah, this is now a broad overview of the methods involved in this data-driven surrogate modeling. We need to relate the parameters of a simulation to its output of interest. So we need to relate the laser power, laser velocity to the gap. The challenge here is that in reality, we not only have the gap as a variable, we might have microstructural information also. So we have a very high dimensional objective function. We have a high dimensionality of the parameter space. For example, the laser power could be a function of the toolpath position. So there's many ways to increase complexities. And also we have very high computational cost because it's a many query task to create this data. And this is why we need also multi-fidelity approaches, not only this high fidelity model, but maybe also other low fidelity models. There are many different machine learning methods available for meta modeling, for example, neural networks, bridging, what's known as Gaussian processes, and others. Another thing, what we need is design of experiments, which helps us to identify the most informative sampling points, and also provides us with adaptive sampling strategies in order to reduce the number of function calls of simulations necessary to obtain the most of the knowledge. Model order reduction is the way which helps us to build these low fidelity models. We needed, as I said, to build a data-driven surrogate model, which is a many query task, and it helps us to decrease the computational cost. So this is rather a summary of the methods. You might be also familiar with them. I just wanted to summarize it. And I'm in contact here with Ulrich Römer. There's no results so far. I hope we can give you an update in the near future about approaches related to additive manufacturing. So that was current state on virtual process planning for additive manufacturing. And now I want to take you a step further to digital twins. So I said the goal is that we need to exploit process, structure, property interaction. And what we have taken into account for that was so far an a priori estimation of the optimal process parameters. Yeah. So this is what we did. This is what we considered, not experiments, but only numerical simulation. But this is the stage where this is situated. But we have neglected one source of information, that is thermal imaging. Here's a video taken from fused deposition modeling, not from the metal process, but still, it's the message is we are neglecting real-time information, and the question is how we can incorporate this knowledge from the process into numerical simulation, combine this knowledge with data-driven methods. The goal is to simulate quantities in real time, or to simulate quantities based on measurement data that we cannot basically measure. We can measure the temperature, but we cannot measure the microstructure. But the microstructure is basically what interests us in the sense of process monitoring. So when we think about functionally graded materials. And this is again the big picture. We have the process, which is influenced by more than 130 parameters, and the actual design. We have different scanning strategies. Yeah, we have on the structural side, we have simulations available for cellular automata to represent the microstructure, but this is currently only possible for only a very few layers. It's not possible for an entire part. And then from this microstructure, we can then apply homogenization techniques in order to deduce properties. But this so far is only feasible for heterogeneous, for microstructures where we have basically everywhere the same microstructure. And when we think about heterogeneous microstructures within functionally materials, we might realize something else. So this first step, process structure interaction, is the topic of a DFG proposal, which is still under review. And the second topic here, structure property interaction, is a topic which I want to address later here in the last section on CNN homogenization. And this real-time information then can help us basically to decode this process structure property interaction, this forward loop. When we have understood this forward loop, we can build a database, and from this database, the idea is to derive optimal process parameters. But this is a long-term goal. The section is named Digital Twin, so I've presented an idea for additive manufacturing, but I want to give a more general introduction about this. So we have here the product lifecycle. We have design and planning phase, we have production and construction, we have an operational phase, and we have inspection and maintenance. We have this in mechanical engineering, but also in civil engineering. It's common. What I have omitted here is the recycling part, but this is the stages which I want to consider here in the digital twin. What we are doing right now with numerical simulation is we are building virtual twins. This is a new name which I found in literature, but I think it's quite nice. It's a virtual model of our product, but it's based here in the design and planning phase. And the idea now of a digital twin is to combine this data arising from numerical simulation and experiments with data from the actual process, from the other stages of the product lifecycle, arising, for example, from metrology. And the goal is to build a complete digital representation of a physical asset in all of its aspects. So generally speaking, the idea of data-driven modeling and simulation for mechanical systems is basically to measure what you can, and then to simulate what we cannot measure. The example from additive manufacturing is temperature, which we can measure, and microstructure, which we cannot. But the question is, how about the physics? And now I want to skip a bit the topic and go into current research activities on physics-informed neural networks. When we think about neural networks, we usually think about data-driven simulation. That is, we think about physics-agnostic machine learning to build empirical relations enabled by model order reduction. We can learn latent space dynamics to build time-dependent problems. And what is common to all of these approaches is that we require big data, which can arise from sensing or from simulations. This is data-driven simulation, and on the other hand, we have the numerical simulation, which provides us with a very sound theoretical background. We have balance equations, we have constitutive assumptions, and also the kinematic relations. So we have a strong theoretical foundation. And also we require very little data only. We have the initial and the boundary conditions, and that's it. Otherwise, we are generating data. And the physics-informed neural networks now aim to combine these two worlds. It has been shown that neural networks can actually do both data-driven simulation, numerical simulation, but they can also both can be combined in a symbiotic manner. And before I go into details, I want to tell you a bit about the history, because actually it's a new approach and this has been hyped in the last years. But the idea is not that young. It has been first presented in Lagarde et al. In 1998 and has been reactivated only recently in 2017, 2018. And automatic differentiation. This was basically the breakthrough here, why it has now widely applied. And what has also happened was the extension to time-dependent programs. I will comment on this automatic differentiation and the importance of automatic differentiation later. First of all, I want to make you familiar with the general idea. The general idea is to take a feed-forward neural network as a global PDE Ansatzfunction in finite elements or finite volumes or many other mesh-based methods. We always have Ansatzfunctions which are defined only on a grid, only locally. And here, the neural network is a global ansatz to the PDE. So before starting with physics-informed neural networks, I want to start with neural networks in general. We have an input, which I denote here x. We have an output, which is denoted v hat. And we have a loss function. And this loss function is used in order to fit these parameters of the network theta. These parameters are associated here with these circles, which are the neurons. They are associated with weights and biases. And these are adjusted then in order to achieve a goal that is to minimize this loss function. In the data-driven training of neural networks, we define the loss function, we define an error, here mean squared error, as the difference between the output of the neural network for a given data point xi minus the according v value of that data point. So we have a data point not only for x but also for vi, and we have an evaluation of the neural network at that data point. And this difference shall become 0. This is the data-driven training of a neural network. And then we adjust the parameters of the neural networks, these parameters thetas, with respect to the loss. So we want to minimize the loss. This data-driven training is also part of the physics-informed neural networks, because also in the numerical simulation we have data, the initial and boundary conditions. And this is how we incorporate them. We enforce the initial conditions. The initial conditions become part of the loss function, and the boundary conditions here become part of the loss function. Now I said we use also a numerical setting here. So we use the neural network as a PDE Ansatzfunction, as a global PDE Ansatzfunction. That means we can use this primary variable here, the output of the neural network. The output of the neural network is defined as the primary variable, and then we can differentiate this output of the network with respect to its input by means of automatic differentiation. And this was the breakthrough in the recent years, that somebody has taken this paper back from 20 years ago, which basically consisted of a long derivation, because they did all this by hand. And deriving this function with respect to its input it's not funny, especially when we know that this structure or this layout of the neural network may vary. So we need to do a hyperparameter search for the optimal layout of the network, for the number of hidden neurons, for the number of hidden layers, the number of hidden neurons per layer. And then this concept has also been applied to time-dependent PDEs in the same manner. We have time here as an additional input. When we have time as an input, we can also differentiate the primary variable with respect to the input. And we can again apply automatic differentiation. This is the one possibility, but there's also the possibility to do it in a discrete time setting. So this is the continuous time setting where we have time as an input, so we can feed and constrain any value we want for the time. And there's also the possibility to represent this temporal derivative by means of an integrator, for example, implicit Wurm-Kutter method. And here now, time is not an input, but we have multiple outputs here that are the different Homogeneous stages and the velocity of the new time step. And all these contributions here from the integrator, from the automatic differentiation, then are fed into the loss function. And this I applied here on fluids. First, I want to comment again on the time integrator. So when we consider the 1D equation of motion, we have we can write the implicit Homogeneous integrator for the velocity. The position is then directly dependent on the velocity, so we take a velocity here as a primary variable. And we have here an expression for the velocity stages, which are associated here to the time steps in between this time interval of the old time step and the new time step. And we have the velocity of the new time step. We have coefficients, AJI and BJ, which we can take from a Bachelor tableau. And we need to train, of course, the neural network. So we need to find an expression of something that we know. And what we know is the velocity of the old time step. So we simply rearrange this equation. We find an expression for the velocity of the old time step, which is a function of each and every Homogeneous stage velocity, and same here for the new velocity. Then we can define the loss function by simply enforcing this difference between the estimated velocity and the real velocity of the old time step to become 0. And what we can see here in this example is that we can realize very, very large time steps. So we start here and use a time step of 10. We can jump over entire vibration cycles. So this is very, very interesting because we can realize very high order Homogeneous interpolants. And this I applied then in a paper of last year for two incompressible Inviscid Euler equations shown here. And the PINN ansatz is then the same. We use an ansatz. We use a neural network as an ansatz for the velocity and for the pressure. So yeah, it's just a physics-informed neural network which takes in the velocity of the old time step, but not as an input. It comes in from the side. As an input is only here the spatial coordinate. We need then, of course, in the particle method, a mapping between the configuration at time Tn and the mapping at configuration Tn plus 1. So yeah, this mapping is defined by the incremental deformation gradient. And what else is to mention is that we can penalize the divergence also and the loss function, which is also quite nice. So far for the theory and overview, and here I want to show you some results. We see here the dam weight problem and also let's say the sloshing example. What I want to emphasize is here for the sloshing is that we have used an arbitrary particle configuration. Yeah. So the spacing here between the particles is fully arbitrary, and this is something very special for particle methods. In SPH or other particle methods, they always fail when the particles somehow become disordered and particle shifting can be applied and so on and so on. So this is really a very interesting feature, and it's related to the fact that we are here dealing with let's say, a global ansatz to the PTE. Ongoing work. This method or these pins can also be applied to inverse problems, and this is what I want to do next. This has also been reported in the literature for other types of problems, mathematical equations, and yeah, the idea is now here to use surface positions, for example, sparse position measurements, in order to reconstruct flow fields. This is yeah, ongoing work. And the main reason is that due to this yeah, global approach here, is that this method cannot really compete with numerical methods, with other numerical methods, because it's too expensive. It's interesting to see, but it's too expensive basically to train. We need to train a neural network, a global PTE for each and every time step. And what is more interesting is then applications where other methods tend to fail, like, for example, inverse problems. This is a current ongoing work in the research training group, Aging of Materials 2075. It's the number, it's less complicated than the entire name. And the topic here has been raised from the Institute for Stahlbau. The idea was to predict structural rest life of buildings. And this is an in situ experiment here. So there's a test specimen which is cyclically loaded, and the idea is now to identify the parameters from these displacement fields here are at distant steps in time. So we just want to monitor in a certain way the parameter evolution with time. For that, we need inverse modeling in order to explain the material parameters. What the Institute for Stahlbau is using is the virtual fields method. And here at IMB, there's a student, David Anton, a doctoral student who wants to apply that with the physics-informed neural networks. This is also recent ongoing work. Another idea is to apply these PINNs in inhomogeneous elastostatics. Also a topic of a PhD student, Alex Henkes. He was working with wood plastic composites, microstructures with polymorphic, uncertain material properties and geometry. And this is also something where PINNs can be very interesting for the forward problem in combination with uncertainty quantification. So when we're dealing with uncertain material parameters, and for the inverse problem in order to identify material parameters. But what I want to focus here on the next slide is rather to show you some implications which arise with the fact that we are dealing with a global ansatz function. And for that, we are using a simple test case, a plate with an inclusion. We have a different Young's moduli in the matrix and the inclusion. And so it's basically an inhomogeneous problem. And we have some error matrix for the FE results, we have FE results, and we have a PINN residual, and we need to identify the optimal network topology in order to apply PINNs with the global ansatz functions to this problem with a high localization. Here are some results. On the top, the FE solution, you see the plots quite smoothly. Also for the PINN, it's smooth. Smoothness is not a problem with neural networks, actually. But we see that we here have some deviations. The overall error is quite nice, or in the range of 1% at maximum, but we can do somehow a better job here on the stress in the y direction, for example. And what we are considering for that is to locally refine these physics-informed neural networks by means of domain decomposition. This has been presented by Yaktab, by the group of Kaniadakis. And they divide the domain into several domains. In each domain is in each domain there's a PINN as an ansatz. And then of course we need stitching conditions for the displacement and also for the traction. And we also need to compute the surface normals. This is one approach which we are currently investigating. I hope we can submit a preprint here or submit something here soon. And the other possibility here is the X-pins, where the continuity is enforced in the residual and the stitching is there performed by an indicator function. And this enables us to really also use, to follow the geometry somehow. Here I did not follow it with PowerPoint, but it would allow to really follow the geometry, and we do not need to compute any surface normals. That was it about the ongoing work on physics-informed neural networks and introduction, and also ongoing works for inverse problems and for the inhomogeneous case. And now I want to focus on a long-term goal. This is a current student project. Computer-aided medical diagnosis is the title. What we have here is an FE model for tumor growth. It's a model which a colleague from Hanover, Maisem Soleimani, has developed and published also. And it has many physical effects. So we see here snapshots of the model. We have here blood, which is a nutrient, provides oxygen and glucose for the tumor to grow. The magnitude of color here refers to the growth, to the growth. And we see that the tumor grows, and then at some point tumor growth stops. The basic characteristics of this models is that we have anisotropic growth. That means that growth is occurring in the direction of the least resistance, and growth is driven by nutrient diffusion, which is provided by the blood. And also the tumor is modeled as an unhealthy tissue, which can have different parameters. And these parameters, this is actually always the crux of these complicated models. The quantity of parameters, it's the growth constants, the competing decay constant. We have a maximum concentration. We have a diffusion coefficient for the nutrient. We have a Young's modulus, Poisson ratio, and a cessation pressure, so the pressure where tumor growth stops. And the idea of this project was to say, how can we actually apply this model in practice? How can we basically make it useful to really assist doctors with diagnosis? And yeah, again, what we need here is parameter identification at time 0. At the day 0, we can take an MRI, and 30 days later, we could take again another MRI. And from these two MRIs, we could identify parameters of our model. And when we have identified parameters, we can make a forecast for the FE simulation, and of course we also need an uncertainty quantification inbuilt because we might not have found the true model parameters. So here we need to really be sure about what we're doing. And what the student is currently doing, he's testing this approach with genetic algorithms. So with the genetic algorithms, we have the issue that we have a many query problem of the forward FE problem. If the model is expensive, this can be cumbersome. And what we also need is image segmentation and meshing, which is required. So when we are working here with, we are not at the moment, but when we would be working with real MRI data, then we would need to really segment the data and mesh it. And the idea here, future potential application of physics-informed neural network would be to apply the PINNs here as an inverse problem. And the benefit would be that we have really the mesh tree character, which enables us to directly use the input of oxen data. So this is yeah, the idea for future research. And now I want to, with physics-informed neural networks, to somehow illustrate the potential for inverse problems. There are other possible applications, but this is what we are currently focusing on. And now I want to lastly comment on computational homogenization with CNNs, that is convolutional neural networks. Here we have an example. We have concrete as a multiscale material. We have a macroscale, we have mesoscale, and we have a microscale. The micro-macro coupling is computationally too expensive for heterogeneous materials with locally adaptive microstructures. This was my school of thought I had. So my PhD student Alex Henkes, who joined, he had another idea now also to apply this to uncertainty quantification. Also, when we have uncertainty quantification with uncertain material parameters, same issue. We have a many query task, and many function calls are very expensive. The idea in CNN homogenization is we take a CT scan, an image, and from this image, we compute an FE mesh. We perform computational homogenization in order to compute effective properties. So then on this axis here, we have the image and we have associated properties and image. And this image can serve as input data to a CNN, and the effective properties as target data to a convolutional neural network. Convolutional neural networks are traditionally used for image classification tasks. So you basically put in an image and then you get out dog or cat, but you can also get out a number and nothing else is going on here. We get in an image and get out an effective property number. Yeah, so as I said, so PhD student here, he has started his PhD in another group and has joined recently this month and also published a paper on this for uncertainty quantification. The challenge that we are facing here is that experimental data for training is very limited. So we need to think about generation of artificial microstructures. This is what we are basically currently doing. Said the conceptual talk. We have, I want to show you how we can apply data-driven modeling here in the loop of this multiscale problem. We have microstructural characterization and testing. We can identify material parameters from that, hopefully with physics-informed neural networks in the near future. And then we can perform a microstructural analysis and computational homogenization using finite elements, Fourier, fast Fourier transform, or physics-informed neural networks. And from that, we generate training data for our convolutional neural network. And this convolutional neural network can then be used in two scenarios. The first is what I presented, multiscale analysis. We combine, for example, finite elements and CNNs, and where we simply plug in this CNN computed effective properties into the finite element model. We are not computing here a material model with a CNN model, only the properties. And we could also use this for material property monitoring. So when after training, we have any real data of the structure available, we could feed it into the CNN and see whether we have failure or not. And this is basically the interesting thing here, that we can create a link between different stages of the product lifecycle, between the design and planning phase and the inspection and maintenance. So this first scenario here was only computationally efficient multiscale analysis. So this is something related here to the design and planning phase. But this material property monitoring really creates a link between inspection and maintenance and design and planning. And this, in my opinion, what digital twins are about, was data-driven modeling and simulation is about, to create links between this, within this product lifecycle. Quick recapitulation. We are coming to the end of my talk. I've talked about virtual process planning for additive manufacturing and motivated from there the need for digital twins. And I presented physics-informed neural networks, current activities here on physics-informed neural networks, and a vision here for computer-aided medical diagnosis, or future field of application, how we could basically use this if we make some effort here in the modeling with the PINNs, and other ongoing work with computational homogenization with convolutional neural networks. And now, as a take-away message, I want to focus again on this product lifecycle. What we are doing with numerical simulation is to build virtual twins. And in my opinion, here these data-driven models, they are not really, let's say, it's not a competition for these numerical methods. It's rather, an add-on. Something is an improvement. It's something which helps to use numerical simulation not only in the design and planning phase, also in the inspection and maintenance, the operation, and in the production and construction. So I think there's a symbiotic between these numerical methods and these data-driven methods, and this is what I want to work on in the future. And I thank you for your attention, and I hope I could give you an overview. Thank you.